Hi everyone, I hope you're all doing well. For this lecture, we are going to go through parts of chapters 12 and 13. We are going to discuss a growth model with technological progress and see how steady state levels of capital per effective worker, output per effective worker, consumption per effective worker, and golden rule savings rate are determined in this model. We will also look at determinants of technological progress and see how technological progress affects employment using the ISLMPC model towards the end. So let's begin. Okay, so in the last lecture, we had a growth model, and in that growth model, we had a production function that consisted of capital and labor as its factors of production. Okay, but in this chapter or in this lecture, we're going to extend that model and allow for a variable A to account for the current state of technology. Including the current state of technology or technological progress in your model is extremely important because it is more realistic. The current state of technology or technological progress leads to larger quantities of output for given quantities of capital and labor. Say you have a given fixed amount of capital and labor in your economy. If you have a good level of technology and if you have technological progress, then given that fixed capital and labor, you're going to be able to produce more than if you did not have that level of technology in the economy. Also, technological progress leads to the creation of better quality products in the economy. Technological progress also leads to brand new products being produced in the economy. And lastly, technology leads to a larger variety of products being produced in the economy. So after including technological progress, this is what your production function looks like. Now your production function includes capital and technological progress times N labor. This AN term here is called effective labor. So the two factors of production that you have in your production function are capital and effective labor. So why is the state of technology multiplied by labor? Well, technological progress reduces the number of workers required to produce a given level of output. And technological progress increases the output that can be produced using a given number of workers. That is, if you have greater technological progress, a fixed number of workers are going to be able to produce more than if they did not have the backing of technology. This AN term, which is your technology times the labor supply, will be what we call effective labor, as I said before. We will now assume that for a given current state of technology, the production function still exhibits constant returns to scale, which is reflected by this equation here. So if you increase capital by 1 unit and increase effective labor by 1 unit, your output will also increase by 1 unit, and so on. We will also assume that the production function exhibits decreasing returns to each individual input, that is, decreasing returns to capital and decreasing returns to effective labor. Okay, so in the last lecture, we looked at output per worker and capital per worker. But in this lecture, what we're going to do is we're going to derive output per effective worker and capital per effective worker. So in order to do that, we will divide the production function by effective labor, that is Y divided by N. So when we divide the production function by effective labor AN, we get this following function. So looking at this function, we can say that output per effective worker here depends on capital per effective worker. In other words, output per effective worker is a function of capital per effective worker, which can be shown by this equation. So your output per effective worker is a function of capital per effective worker. So in this lecture, we are going to assume that the labor force is growing at a constant rate, and this constant rate is GN, which is the growth of labor force. And technology is also growing at a constant rate, and we will refer to that as GA, growth of technology. Okay? Now, remember that your total savings is some proportion S of your total income or total output. And in the goods market, we found out that investment is equal savings. So if S is equals lowercase s times income, your investment is the same. So investment equals savings rate times income. Okay, but now we want our variables in effective labor or effective worker terms. So we will divide each side by effective labor to get this equation. So I divided by AN equals S times Y divided by AN. Okay, so now from this equation, we know that output per effective labor is a function of capital per effective labor. So we will plug in this for output per effective labor and then get this equation. And we need to remember this equation that investment per effective worker is equal to savings rate times function of K divided by AN, or capital per effective worker. Now we are doing all these steps to find out the evolution of capital accumulation. Okay, so before we do that, we need to go through a few more steps. Okay, first we will look at the evolution of technology. Okay, so this part is about technology and this part is about labor supply. Okay, so what this equation, the first equation, tells us is your technology at time t plus 1 is equal to technology at time t plus the amount that your technology grew in time t. So AT times the growth rate of technology. Okay, so that's your evolution of technology. You can rearrange that equation to get it in terms of technology at time t. So technology at time t is equals to technology at time t plus 1 divided by 1 plus growth rate of A. You can do the same for evolution of labor. So this equation here tells us that your labor supply at time t plus 1 is equal to labor supply at time t. I'm sorry, this is a typo. Labor supply at time t plus 1 is equal to labor supply at time t plus the amount that your labor supply grew at time t. So your total labor supply at time t times the growth rate. Okay, so this is your evolution of labor, and you can rearrange this equation to make it look like this. So your labor supply at time t is equals labor supply at time t plus 1 divided by 1 plus growth rate of your labor supply. And we will need these equations to find out the evolution of capital accumulation in the next slide. Now, we assume that technology over time grows at a constant rate of GA, and labor over time grows at a constant rate of GN. Okay? So, it follows that the growth rate of effective labor, AN, is equal to the growth rate of technology plus the growth rate of labor. Therefore, the growth rate of effective labor is GN plus GA. Now let's look at what our equation for capital accumulation looks like. Okay, So this equation tells you the evolution of capital stock, or this is the equation for capital accumulation. Okay, you can call them both. So capital at time t plus 1 is equals capital at time t minus the depreciation plus the investment into new capital. Okay, so in the last lecture we divided this capital accumulation equation by n, but now we want it in terms of effective labor or effective worker, so we will divide both sides by an, effective labor. Okay, so notice how there is a t subscript on both a and n, because now we are assuming that both technology and labor supply is growing, so they have time subscripts. In the last lecture, n did not have any time subscript because we thought of labor as not growing. Okay, it was constant, but now it is growing. Okay, next step is that we want this term to be consistent throughout, and we want this term to contain t plus 1 for all subscripts. Okay, so remember that we worked on equations a, t, and nt in the last slide, which were in terms of at plus 1 and nt plus 1. We will plug those in here. And once we plug those in here, our left side of this equation will look like this. Okay? So if you have a paper and pen, you can just do it yourself on your notebook. Okay? So once we have this left side looking like this, we want it just in terms of Ka and N. So we will divide again both sides of this equation by 1 plus Ga times 1 plus Gn. Divide both sides by 1 plus Ga times 1 plus Gn. Okay, then we get this equation for evolution of capital stock. Okay. The next step is to subtract Kt over At times Nt from that equation for evolution of capital stock. And once you do that, your equation of capital stock will look like this. Okay, and then at the steady state, remember that at the steady state, Kt plus 1 is equals Kt equals K star. So you can denote the steady state as K star as well. But we can keep things simple and just denote it as K. So at the steady state, Kt plus 1 over At plus 1 times Nt plus 1 is equals K over An, and then Kt over At times An is also equals K over An. Also in the steady state, your time subscripts go away for this equation as well, so It over At times An becomes I over An, which means at the steady state, none of these variables are growing, they are constant. So we need to plug in these steady state conditions into the equation for capital accumulation here. And then so this becomes K over An, this becomes K over An, so this entire thing becomes 0. Okay, and then the right side, the denominator will be multiplied by this 0. And so what you'll be left with is this top portion once steady state is imposed, and then at the steady state this term is equals I over An, and then this term is K over An, and so your steady state eventually steady state condition eventually looks like this. So your investment per effective worker is equal to capital per effective worker times this term. This is your depreciation rate, this is the growth rate of technology, and this is the growth rate of labor supply. The equation in the last slide can be graphically shown by this graph, okay, where the right side of that equation is the required investment, and when this required investment intersects with the level of investment at this point, that is your steady state. So at this steady state, this is your capital per effective labor or effective worker, and this is your output per effective worker. Now imagine that you were not in the steady state. Okay, so imagine that the level of capital stock in the economy is here. Okay, so you are at this point in the economy. At this point, see that the level of investment here is greater than the level of required investment. The level of investment into capital is greater than the level of required investment into capital, which means capital stock will keep increasing because your investment into capital is greater than required investment, so your capital stock will keep increasing, and it will keep increasing till the capital per effective worker reaches the steady state level. Okay, again, if your investment is less than your required investment of capital, okay, again, we are not at the steady state. We have a capital stock that is higher than the steady state capital per effective worker. At this point, we have a required investment into capital which is greater than your actual investment into capital stock. At this point, because your required investment is higher than actual investment into capital, your capital stock will keep decreasing. It will decrease and will keep decreasing till capital per effective worker reaches the steady state level. A few things to remember here is that in the steady state, the growth rate of output will equal growth rate of technology and growth rate of population. So in the steady state, growth rate of output is equals growth rate of technology plus growth rate of labor supply or population, and the same goes for growth rate of capital, which is again equals growth rate of technology plus growth rate of labor supply. Two important observations that you need to remember. First, capital per effective worker and output per effective worker are constant in the steady state, which means that in the steady state, growth rate of capital per effective worker is equal to 0, and growth rate of output per effective worker is also equal to 0. Why? Because growth rate of capital is equals GA plus GN, and growth rate of effective labor is also GA plus GN. So for the full term here, our capital per effective worker, it's not growing at all. So growth rate of capital per effective worker is equal to 0. And for the same reason, because the numerator grows at GA plus GN and the denominator also grows at GA plus GN, growth rate of output per effective worker is 0. In the same way, capital per worker and output per worker are growing at the rate of technological progress. How? So this is your capital per worker, and notice that we are not looking at capital per effective worker, we're looking at capital per worker. So capital per worker, your numerator here, capital is growing at GA plus GN, and your denominator N is growing at GN. Therefore, capital per worker completely is growing at GA. Okay. In the same way, because the numerator here, growth of output is GA plus GN and growth of labor is GN, the residual is GA, so both your capital per worker and output per worker are growing at the rate of technological progress. This table here shows the characteristics of a balanced growth path or characteristics of an economy at the steady state. So here you can see that there are all the growth rates that we were talking about in the last few slides. So remember that technology is growing at GA, labor is growing at GN, capital per effective worker is not growing, output per effective worker is not growing, capital per worker is growing at the rate of technological progress. The same is true for output per worker. And then obviously we know that capital is growing at GA plus GN and output is growing at GA plus GN. You need to remember these for this chapter or for this lecture. Now we're going to look at the effect of changes of savings rate on steady state level of capital per effective worker and output per effective worker. You should know that changes in the savings rate do not affect the long run growth rate. However, changes in savings rate do affect the long run steady state level of output per effective worker. Okay, now let's look at this graph. Imagine that we are at the steady state. Okay, so we are at this level at the steady state where your required investment is equals the level of investment into capital that you have. So we're looking at these two curves right now. So at this point, your steady state level of capital per effective worker is K over AN 0, and steady state level of output per effective worker is Y over AN 0. Okay. Now suppose that the savings rate increases from S0 to S1. Okay, this causes the investment curve to shift upwards, and your new steady state level is at this point. Okay, at this point your new steady state level K over AN 1 and output per effective worker is Y over AN 1. Therefore, when you are at the steady state, an increase in the savings rate is going to increase the level of the steady state level of capital per effective worker, and it is also going to increase the level of the steady state level of output per effective worker, but not the growth rate. Our next step is to determine the golden rule savings rate. Remember that in the last lecture, we found out the golden rule savings rate by maximizing consumption per worker. Here, to determine the golden rule savings rate, we will maximize the consumption per effective worker. Okay, so at the steady state, consumption per effective worker is given by this equation, which is basically your income minus the level of savings or investment in the economy. So the first step to find out consumption per effective worker at the steady state is to find out capital per effective worker at the steady state. And in order to do that, we're going to use this production function. This is your standard Cobb-Douglas production function. And then using this standard Cobb-Douglas production function, we will plug in our steady state condition. Once we have this equation, we can bring all the capital per effective workers on one side and all the other parameters on the other side, and then solve for K star over AN, or capital per effective worker. Raising both sides of this equation to the power 1 over 1 minus alpha, we get this equation for capital per effective worker at the steady state. Once we have our capital per effective worker at the steady state, we can plug that equation inside this equation for output per effective worker at the steady state and find out output per effective worker. Therefore, at the steady state level, Y star over AN, or output per effective worker, looks like this equation here. Now that we have the equations for capital per effective worker and output per effective worker at the steady states, we can plug those into consumption per effective worker and find this equation for the steady state consumption per effective worker. Now that we have this equation, the next step is to find the savings rate that maximizes consumption per effective worker. And to do that, we need to take the derivative of this consumption per effective worker with respect to the savings rate, and then equalize that to 0 and solve for the savings rate. Taking the derivative of consumption per effective worker and setting that equals 0 gives us this equation. Using this equation, we can solve for S and find out the golden rule savings rate, which is the savings rate that maximizes consumption per effective worker. Using this expression and then solving for S gives us a savings rate of alpha, which is the relative share of capital in this model. Recall that this is the same savings rate that we found in the last lecture when we were using a Cobb-Douglas model without technology. So the takeaway from here is, if your production function is a Cobb-Douglas production function, then your savings rate will always be equals alpha, the relative share of capital in the economy. So what are the determinants of technological progress? When we think about technological progress, in our heads we're imagining massive breakthroughs, invention of the microchip, self-driving cars, a satellite that can survive going through the black hole, etc., etc. However, the truth is that most technological progress is very slow, very monotonous, and it's the result of research and development that most companies conduct. And most firms spend on research and development to create new products, find out faster methods of production that reduces costs, creating a variety of goods, increasing efficiency of products, like car companies are always trying to make cars that are more fuel efficient, and all of this would increase firm profits. Research and development produces ideas. And unlike investment in capital, production of ideas is neither excludable nor rivalrous. Recall what excludable and rivalrous mean. Excludable means that if a firm has a certain idea or a production method, it cannot stop other firms from using the same idea, because there's always the possibility that other firms may find out about the results of one firm's research and development. Research and development or production of ideas isn't rivalrous because one firm's use of a particular production method or idea does not stop another firm from using the same idea. There is not less of that idea left for another firm. So it's not rivalrous either. Therefore, research and development spending depends on the fertility of research, or how easy it is to turn ideas into new products, and the appropriability of research, that is the extent to which firms can profit from the results of their own research and development. The fertility of research, or turning ideas into products, depends on the interaction of two types of research. One is basic research, where the ideas are being made, and second are the people who apply those research ideas. So basic researchers like a chemist or physicist would work with other people who work on applying that research and development into creating new products. So research and development ideas and production ideas are not excludable, meaning that if you as a firm are using a particular idea or production method, you cannot stop another firm from using it. But if another firm is using it, you don't have that specific edge that you would have if no other firm was using the same technology. Which means if everyone's using the same technology, you're not actually making any profits. But if firms cannot make profits from the development of new products, they will not have an incentive to spend on R&D or to spend on research and development and come up with new products. This is the rationale behind intellectual property and patent law. Patents give protection to a firm, and they give them a temporary monopoly to using a product that they patented. Patent protections give firms the power to profit from their own labor or their own research and development. However, there is a trade-off involved here. The stronger the patent protections, the more profits or rents firms can extract from research and development. However, there are certain fields such as medical research, pharmacy, where we want life-saving drugs or life-saving innovations to be widely available to people at the lowest possible cost. But if firms have patents on their products, they are definitely going to charge a price that's way higher than marginal cost. For example, when the first ballpoint pen hit the markets, it was patented and cost around $12.50 or $12.50, which is equivalent to $150 today. Ballpoint pens are not very life-saving, but this can be also applied to life-saving drugs, machines, other medical supplies. Therefore, it is the job of policymakers to find the perfect level of patent protection to maintain incentives for firms to invest in research and development, but also have consumer interests in their mind for certain innovations. Recall the production function that we used in chapter 7, where we said that our production function is equals this expression, y is equals n, in which we can say that the level of employment in an economy depends on the equilibrium output. Now we will change and use the following production function by allowing for technology in our production function. And we can rearrange this production function to look like this. So employment now depends on both equilibrium output and the state of technology. The higher the equilibrium output, the higher will be your employment level in the economy. Or what is the effect of an increase in the state of technology on equilibrium employment? We will answer this question by looking at the ISLM-PC model. So, if there is a major invention and it is widely adopted, then the current state of technology will increase. If the current state of technology increases, this is likely to lead to increased autonomous consumption due to more optimism about the future, and additionally it would lead to higher investment by firms because of that major invention. In this case, your IS curve will shift to the right. IS curve shifts to the right, and the equilibrium level of output increases. And as the equilibrium level of output increases, employment is also likely to increase. Okay, so an increase in the level of technology or current state of technology due to a major invention is likely to increase the level of employment in an economy. But if the increase in current state of technology is due to an increase in efficiency in the production process, one that reduces the need for as many workers in the production process, there may be pessimism about job security. This may lead to decreased consumption and increased savings to insure against that risk, which would correspond to a leftward shift of the IS curve. So your IS curve shifts to the left. If your IS curve shifts to the left, then output shifts to the left, which means that there is a decrease in the employment level in the economy. So an increase in current state of technology in this case is leading to a decrease in the employment level in the economy. Now let's look at the impact of an increase in technological progress or current state of technology in the aggregate demand, aggregate supply model. So, following an increase in the current state of technology, both aggregate demand and aggregate supply curves will be affected. If technology increases, that decreases the amount of labor needed to produce a unit of output, thus decreasing cost for firms. This leads to firms reducing their price at any given level of output. Thus, the aggregate supply curve shifts downwards. The aggregate demand story is not as straightforward. The effect of an increase in current state of technology on aggregate demand curve largely depends on the type of innovation we are talking about. If we think about the first case, when there is a major invention and it is widely adopted, this situation would likely lead to an increase in autonomous consumption due to more optimism about future growth. Additionally, it would also lead to higher investment by firms. In this case, the aggregate demand curve shifts to the right. However, if this increase in technology is because of increase in efficiency, there might be pessimism about job security, as we discussed before. This leads to decreased consumption and increase in savings to insure against that risk, which would correspond to a leftward shift in the aggregate demand curve. But even if aggregate demand shifts to the right, we can't be certain that the new equilibrium will increase output enough to maintain the same level of employment. The eventual effect on output and employment will depend on the relative strengths of each shift of each curve. So we are done with this lecture. Please feel free to email me for questions. Bye.